In this question, we're going to make use of Darcy's equation in order to solve for the energy loss through a length of straight pipe. So let me just start by reading the question. We're going to compute the energy loss as zero point 0.2 foot cube per second of water flows through a length of 80 feet of 2.5-inch Schedule 40 steel pipe. So here is my 80 feet of straight pipe laid out horizontally. So the length of the pipe L is 80 feet. And we're told that this is 2.5-inch Schedule 40. So from the Schedule 40 steel pipe data table, you can find that this pipe has an inside diameter of 0.2057 feet, and it has a cross-sectional area of 0.03325 feet squared. And the water is flowing through this pipe, so I'm going to draw it as entering from the left, and it has a volume flow rate Q of 0.20 feet cubed per second. And we want to make use of Darcy's equation to solve for the energy loss due to friction as the fluid flows through this pipe. So let me first start by just reminding you what Darcy's equation is. It's the energy loss, H sub L, equals a friction factor F times the length of pipe over the inside diameter of the pipe times the velocity head, V squared over 2G. So the only thing that's a little bit subtle about Darcy's equation is the friction factor. And the method that we use to determine the friction factor depends on the type of flow that we have in the pipe. So if we find that the Reynolds number is less than 2000, that tells us that the flow is laminar. And if the flow is laminar, we have an algebraic expression for the friction factor. This friction factor is just equal to the number 64 divided by the Reynolds number. And that's very straightforward to calculate. However, if we find that the Reynolds number in the problem is greater than 4,000, the flow in that case is turbulent. And the friction factor we will get from what's known as the Moody diagram. Okay. So the first thing that we want to do is calculate the Reynolds number so we could determine whether our flow is turbulent or laminar. So the equation for the Reynolds number for a round pipe is equal to the velocity, the average velocity of flow in the pipe times the inside diameter of the pipe divided by Greek letter nu, the kinematic viscosity of the fluid traveling through the pipe. And in that case, that's water. And from the properties of common liquids, you can look up that the kinematic viscosity of water is 9.62 times 10 to the minus 6 feet squared per second. Now, we aren't given the velocity, but we are given the volume flow rate, and we can relate the two by the fact that the volume flow rate Q is equal to the average velocity in the pipe times the cross-sectional area of the pipe. So we can rearrange this to solve for the velocity. We find that V is Q divided by the cross-sectional area A. So that's 0.2 feet cubed per second divided by 0.03325 feet squared. And you'll notice that the feet squared cancels with 2 of the 3 feet in the numerator. And when one works this out, I find about 6 feet per second, or more precisely, 6.015 feet per second. I don't think you need to keep all those significant digits, but I will do that just to be extra careful. 6.015 feet per second. That's the velocity, the average velocity of the water in the pipe. So now that we have that, we can go and calculate the Reynolds number and R. Again, that's V times D over nu. So in our case, that's the 6 feet per second times the inside diameter, 0.2057 feet, divided by the kinematic viscosity, 9.62 times 10 to the minus 6 feet squared per second. And what you notice is that we have 2 powers of feet in the numerator, feet squared, and that cancels with the feet squared in the denominator. And we have 1 over second in the numerator, cancels with the 1 over second in the denominator. This leaves us with a dimensionless number, which is good because the Reynolds number is dimensionless. And when you work this out, I get about 130,000. So this is 1.3 times 10 to the 5. So clearly, we see that the Reynolds number in this case is much larger than 4,000. And what that tells us is that the flow is indeed turbulent. So the next step, now that we know that the flow is turbulent, we can find the friction factor F from the Moody diagram. So let me now pull in a copy of the Moody diagram, and I'll put the link below for the same version of the Moody diagram that I'm using. So let me just zoom in here. And what the Moody diagram shows is the friction factor in the y-axis as a function of the Reynolds number in the x-axis, and it shows that for a number of different pipe relative roughness. So the relative roughness is that ratio of epsilon over d. So let me just write that down. Epsilon over d is known as the relative roughness. And we need to find what the relative roughness is for the pipe in question for our problem. And what I like about this version of the Moody diagram is that the roughness is given for a number of different common pipe materials. For this particular question, we're going to be interested in common steel, and we're working with the US system of units, and we see that the epsilon, the roughness for common steel, is 0.0018 inches. So now that we have that, we can go and calculate our relative roughness, epsilon over d. In our case, that would be the 0.0018 inches divided by the inside diameter. And you want to make sure that you use the inside diameter in inches and not in feet as is written above. So doing that conversion, the inside diameter in inches is 2.4688 inches. And when you take this math, you find that this is 0.00073. So the relative roughness in our case is 0.00073. And unfortunately, well, not unfortunately, it's almost never going to be the case that your relative roughness that you calculate will be exactly one of those roughnesses that are available in your Moody diagram. So what do? Well, what you do is you look and try to find the closest value that's available in order to make an estimate. There is a relative roughness of 0.001. That's this one here. That is above the roughness that we calculated. There's also one at 0.0005, which is slightly less than the roughness that we calculated. So we expect that the curve that we would like to see here would actually fall somewhere in between these two. And we'll use both of these curves to help us find the estimate of our friction factor. Now, the x-axis is the Reynolds number, and our Reynolds number was 1.3 times 10 to the 5. And so here we have 10 to the 5. This point here would be 2 times 10 to the 5. So our Reynolds number falls in between there, and it's going to be about here, I would estimate. So let me draw a vertical line where I expect that Reynolds number to fall. So I expect that my Reynolds number of 1.3 times 10 to the 5 will look something like that. So that line corresponds to my Reynolds number of 1.3 times 10 to the 5. So now what I do is I look at my curves that I selected. Let me start with the upper one, the 0.001, and I trace this curve back until it intersects with that Reynolds number curve, which is the point right here. I'm also going to look at the lower curve, 0.0005, and trace that one back to where that intersects with our Reynolds number, which falls about there. So I would expect that the true value would fall somewhere in between those 2 points. And if I trace that back by drawing by drawing horizontal lines, I would expect my friction factor to fall somewhere there. And I'm going to just take a friction factor of 0.02 because that's pretty close to being in between those two lines. And there are calculators available online. And if you use those calculators, you'll find that you do indeed get a friction factor of about 0.02. However, I wouldn't jump to use those calculators. It's extremely important that you know how to read a double log plot and extract the friction factor from the Moody diagram. So we're going to use a friction factor of 0.02. I'll put a box around it just so that we could just remember that that's the friction factor that we extracted from the Moody diagram. You might get one that's slightly different depending on how you estimate those curves. And now we have everything we need to go back and calculate the friction loss. So we're going to go back, and I'm just going to write down again Darcy's equation. H sub L equals F, the friction factor, times the length of pipe divided by its diameter, times the velocity head, v squared over 2g. So F is 0.02. The length is 80 feet, divided by the diameter in feet, 0.2057 feet, times the velocity head. The velocity head will be our velocity squared, 6.015 feet per second, and that quantity is squared, divided by 2g. 2 times 32.2 feet per second squared. Let's take a careful look at the units here. I see that feet cancels with feet. I see that 1 over second squared cancels with the 1 over second squared. And I see that feet in the denominator cancels with 1 power of feet in the numerator. So in the end, all of this boils down to dimensions of feet. And when I work this out, I get H sub L equals 4.4 feet. And that's our answer for the energy loss due to friction. The interpretation of that is that H sub L is 4.4 foot-pounds per pound, which is essentially just a way of saying that for every pound of fluid that flows through our system, 4.4 foot-pounds of energy is dissipated due to friction. But again, the final answer would just be expressed as a head, which would, in our case, be 4.4 feet.